And you can use my computer.
Okay.
Just share your access with me.
Perfect. Thank you.
Yeah. Awesome. So also very welcome Marcus and also Marcus' dad here.
Hello all. Thanks for having me.
Were you able to share? Okay. So Marcus is a Stanford SymSys undergrad, finishing up this quarter. His technical interests range from math engineering, formal verification, game design, and human-computer learning. He enjoys a lot of video board and card games, taking walks, playing sports with friends, and trying to design a future where all things can exist in harmony, which is awesome. Yeah, take it away.
Okay. So, all right. This is my senior capstone project. So I'm an undergraduate, and I'm graduating this quarter. And at the start of the quarter, I was talking with one of your graduate students, Francois, who I guess is not here today, about an optimization algorithm that he was working on, which was supposed to sort of make training recurrent neural networks viable. Now, what's the context of this? So transformers have sort of taken the world by storm. They're used in all large language models that we use. There's like video and vision transformers as well. They've been very successful, but from a theoretical perspective, they have a couple of downsides. The main one being that the attention mechanism requires a context window, and the transformer sort of scales with the square of the length of that context window, right? You need the square of that many parameters, and then you also need to process all of that as well per token. So what we would like to do is, if it was possible to make recurrent neural networks viable, then they might have some of those theoretical benefits of just being able to process input in a sort of linear time, right? Unfortunately, training recurrent neural networks has had problems historically. The main one being the vanishing exploding gradient problems. I'm guessing all of you are familiar with that? Okay, great. So, what SPSA is trying to do is it's trying to be a zero-order version of an optimization algorithm. So instead of needing to calculate the gradient, you can just basically sample the function at different points and then use that to sort of, in this case, estimate the gradient that can then be used to do learning, to make a gradient the next step. And that's sort of the promise of it. And in the original paper, they found that on a number of problems, it performs at par or even better than traditional training methods for recurrent neural networks, specifically because of these sorts of gradient dynamics. And so what I wanted to do is to basically test out this algorithm, because I'm also sort of new in this space. Is to test out this algorithm on a small problem, on a simple sort of network architecture, just to sort of see how things work and look at all of that. I think of interest is that the estimator itself is unbiased, so it will, in expectation, it will always sort of reproduce the original gradient, and that the variance, there's a typo there, but the variance or the distance from the true gradient sort of follows this epsilon to the fourth, plus 1 divided the number of perturbations. So how do the perturbations work? How it works is when you have your set of parameters theta, what you do is you, let's say 32 or 64 different directions in gradient space, randomly chosen, and then you sample in that direction and in the opposite direction. And you sort of use those two directions to create an unbiased estimate. This sort of allows you to kind of get around some second order terms that might appear, let's say. And so that's sort of what this n pert is the number of perturbations is also a sort of factor in the distance from the true gradient, which will come up later. Okay, so I decided to try and train LSTMs, so just long short-term memory networks, on to read in a sequence of tokens and reverse them. Pretty simple. some technical details. There's 4 administrative tokens and then content tokens for a total of n plus 4 tokens. In my final work and in all the graphs that you'll see here, I'm using a vocab size of 12, which is kind of small. But even under these conditions where I'm sort of having it reverse effectively 8 content tokens, the length of the sequence is also randomly chosen, and in this case the min length is 1 token and the max length is 3 tokens. And I found that even in such conditions, it was difficult to get the network to converge quickly. Reverse SAS was chosen because I thought it would be sort of easy for the model to do. If you're interested in the details, we can go into that. Here are some details about how the network is constructed. It's sort of a small network that was chosen from the sort of code base of the original paper. I decided to sort of modify the code so that it would all feed into that the algorithm would basically report back just the gradients. It would like fill in the gradients of the parameters, and then take a stochastic gradient descent algorithm. I'll get to that. There's another thing there, but I'll get to it later. So here we can actually see some of the loss curves of training this network on this task. All of the sort of colorful curves are different variations of SPSA with different kinds of hyperparameters. We see that this one starts to diverge, but the best one has some hyperparameters here. I'm not sure if you guys would find the exact hyperparameters interesting, but I do think what's interesting is that compared to stochastic gradient descent, it trains much faster. And critically, this is a loss versus time curve, because when you change the number of perturbations or you change the batch size, each step takes longer, and so you might get better results, but you're actually paying for those results. And so that's why I felt like this was the fairest comparison between the 2 algorithms. That being said, when you analyze them in terms of loss per step, we actually see that SPSA is far more competitive, which is sort of interesting. It's saying that this algorithm is in theory not, on this task, is not actually that much worse than standard gradient descent. It's just that it takes a long time to compute each step because it's doing all these perturbations. But I also wanted to sort of think about what maybe other things that could be of interest to study here. And so one thing that I looked at was trying to look at the gradient norm and the cosine similarity with the true gradient, to sort of understand, like, okay, if I compare these from a theoretical perspective, like they're both sort of suggesting this gradient to move in, how do they sort of match up there? And so this is a gradient norm versus time graph. You can just sort of see, the gradient norm for each of the runs over time. What's striking is that they all have very high values, whereas the stochastic gradient descent one is actually a very small value. It seems to range from about 2.7 at the start and decreases. That model actually converges, and so it basically decreases to 0. But all the other ones, don't converge and are like orders of magnitude higher, right? And so, okay, like maybe there's a bug in the code. Well, if you test the initial conditions of the model and you calculate the gradient norm for different numbers of perturbations at the initial conditions of the model, you do see that at these very, very high numbers of perturbations, this is like 32,000 perturbations, it actually does sort of start to converge to the true gradient norm at that point. And so it seems like that one, if you remember from before, there was like an O of 1 over n perturbations term in the I guess the distance from the true gradient. The math works out where it's basically the same here. That is actually a very high number. In this case, that sort of dominates the epsilon term. And so I thought that was striking. I also decided to look at the cosine similarity over time. What's interesting here is that these curves seem to be a lot more stable. They seem to be mostly constant over the course of the run. And of course, I didn't show the gradient, just the stochastic gradient descent one, because that would be 1. But these values are like 1%, 2%. They're really, really small, which means that the direction is like mostly orthogonal. However, it does happen to work out that because it's mostly orthogonal, but it's scaled up so much, it is still technically a unbiased estimator of the gradient, but it's difficult to see how the model would be able to effectively optimize under these conditions. So what I did is I created a simulation. And here's cosine similarity. It also sort of increases towards 1 as you increase the number of parameters. So I decided to run this experiment where you take the standard gradient and then you just add noise to it, and you try and figure out like, okay, is the model able to optimize under these conditions? The reasoning is that, SPSA has a lot of sort of internal details of how it works, on how exactly it calculates the perturbation, but, okay, thank you. But like, what if we could sort of create those conditions in a more artificial way? How would that work? Here's a bunch of details on how it's implemented. And what we see is that it actually performs worse, which is interesting. This sort of autograd plus noise system is less stable than SPSA. And so, here in, I guess, yellow or tan, we have the SPSA run, and then in this like dark blue, we have the corresponding autograd plus noise run with the same hyperparameters, and it diverges very quickly, which is interesting. You can have the learning rate, and it converges, or like it starts to converge, but it sort of eventually decays. And this is in terms of steps. Now, you might sort of criticize like, okay, well, maybe if you'd run the tandem one longer, it would also have diverged in a similar way. That's fair. Those are experiments I could run. But I think what I sort of learned from this is that SPSA it's not like unsavable, like, and there might also be cases where it does perform better, especially cases where the standard gradient descent performs worse. It might sort of, retain some viability in those cases. But in this case, it was definitely just strictly worse than the autograd. I also did sort of touch on other kinds of optimization methods, like stochastic gradient descent is like not the gold standard, Adam is the gold standard. And I didn't include graphs here, but training this on Adam is even faster than stochastic gradient descent. Interesting future directions is, can you feed something like SPSA into Adam? Or are there ways of sort of reducing the noise with something like a momentum technique that would allow it to train faster? These are things that I think would be interesting. Also of interest is trying to figure out like, okay, why is there this difference between SPSA, which is inherently noisy, and just a strictly like autograph plus noise algorithm? Why is SPSA more robust in these cases? Yeah. So I think that this work does point in the direction that SPSA is not maybe a viable algorithm. But that being said, this is just one small work, and there's a massive literature that studies this. So that's my talk. Let me know if you have questions. Yeah.
Thank you for your talk. At the first part of your talk, you motivated this by the memory requirements, not about speed, right? So I guess for the
Transformers versus recurrent neural networks.
Yeah, exactly. So could it be that for much larger problems this would be more viable, but for like the smaller toy problems, then it doesn't bring that benefit?
I guess so it is a memory problem, but it's also a time problem. In some sense, if you really wanted to have like, like hundreds of thousands of like context windows, right? That would be very time expensive to compute and process. So that's why people don't do that. I think separately there's a training cost method, and so maybe because transformers are more amenable to backpropagation, they might be faster to train, which does have benefits. But I did want to sort of clarify your question actually.
Yeah. I guess the benefit would be really where you're more you can afford to run your training over a longer period of time, but your hardware is limited in terms of memory. Right? Maybe you can't afford to have a H100 or better.
Yeah.
Right? But you can afford to train for a longer period of time. That's okay. But
And so
don't
you
have
sort
like
of
a
sacrifice model size
exactly. Right.
with a sort of recurrent neural network. Okay, I can see that.
Thank you.
Great, thank you.